High above a silent factory floor in upstate New York, vertical towers dropped thin strands of liquid glass through intense heat at 20 feet per second. Air blowers roared inside the facility as giant furnaces radiated heat across the floor. Quietly, plainclothes FBI agents walked past heavy lathes toward an engineer hiding secret blueprints inside a leather briefcase. The agents moved quickly, avoiding any scene on the noisy shop floor. Inside the briefcase lay blue-line drawings, chemical formulas, and small spools of glass thread no thicker than a human hair. Without raising their voices above blowers, federal officers arrested the engineer and seized every file in his desk. What were foreign spies trying to steal from this quiet factory? They were not looking for military radar secrets, nuclear codes, or jet fighter designs. Instead, foreign espionage rings risked decades in prison for a manufacturing process capable of bending light across entire oceans. Spies knew that whoever controlled this fragile material would rule global communication. The glass thread was thin enough to snap between two fingers, yet so pure that a solid glass block 3 miles thick would look as clear as mountain air. If you looked through a window of this glass 3 miles thick, you could see someone on the other side as clearly as if they stood right beside you. Welcome to Rivet and Rebar, where we uncover heavy machinery, forgotten history, and engineering sagas that quietly built our modern world. If you love deep industrial stories and precision tools, take a quick moment to like and subscribe to support our channel. Your support helps us bring more forgotten sagas back to life. Long before federal agents raided that factory, the story began in a smoke-filled river valley surrounded by steep hills. In 1851, an ambitious glassmaker named Amory Houghton Senior established a glass shop in Massachusetts, moved to Brooklyn, and settled in Corning, New York in 1868. Corning was an ideal home for heavy industry. Coal barges floated down nearby canals, quartz sand sat in rich deposits along riverbanks, and timber covered surrounding mountains to feed furnace fires. Standing before brick furnaces burning at 2,700 degrees Fahrenheit, master glassblowers called gaffers worked in brutal heat day after day. Inside a 19th century glassworks, smoke filled the air, iron tools grew scorching hot, and workers sweated constantly in front of roaring fires. Dip a long hollow iron blowpipe into a crucible of white-hot liquid sand, and you pull out a glowing mass of soft glass. Gaffers rolled hot glass back and forth on heavy iron marver tables to shape it. Then, using pure human lung power, they blew air into the pipe, inflating glowing glass teardrops into lantern lenses, oil lamp chimneys, and chemical jars. Exhausting physical work set a strict limit on how much glass a factory could produce. Even a skilled 3-man team could only blow a few hundred glass pieces during a brutal 10-hour shift. A glassblower's lungs gave out long before the roaring brick furnace ever cooled down. Winter brought a famous visitor to Corning in 1879, when 32-year-old inventor Thomas Edison arrived with an urgent mechanical dilemma. Edison had spent months developing an electric light bulb using a glowing bamboo thread, but he hit a physical wall. Standard blown glass bottles were thick, irregular, and filled with internal heat stresses that cracked as soon as the electric filament glowed. Edison needed an exceptionally thin, uniform, airtight glass shell that could shield his delicate filament without breaking. Flawless handwork saved Edison's famous invention when a Corning master glassblower named William Woods stepped up to the furnace. Woods dipped his hollow iron pipe into the liquid glass and puffed a freehand teardrop bulb with perfectly even walls. Edison had his light bulb envelope, and Corning unlocked a legendary partnership that altered human civilization forever. Millions of electric light bulbs were needed across the globe, but relying on human lungs was a financial dead end. By the early 1920s, cities were stringing electrical wires everywhere, and factories wanted artificial light for night shifts. Yet a team of 3 glassblowers, working until their lips bled and lungs failed, could produce at most 1,200 bulb shells in a full day. Electric light bulbs remained expensive items, and power companies were trapped because hand-blown glass could not scale up to meet world demand. Two brilliant Corning engineers, William Woods and David Gray, set out to break this bottleneck by building a machine that could blow glass automatically. In 1926, after 5 years of ruined iron castings, failed timing cams, and sleepless nights in the drafting room, they unveiled the Corning ribbon machine, a colossal beast made of heavy cast iron beds, smooth roller bearings, and water-cooled steel blowheads. The machine executed a fast mechanical ballet that changed manufacturing forever. Picture a continuous stream of white-hot liquid glass pouring from a massive furnace forehearth at 2,000 degrees Fahrenheit. The liquid glass moves constantly, glowing bright orange as it flows out of the furnace. First, the liquid glass stream passes between two water-cooled brass rollers, flattening into a glowing glass ribbon that travels horizontally at high speed across the factory floor. Second, the hot ribbon moves onto a steel conveyor belt filled with circular holes. As the ribbon glides over the belt, gravity pulls small blisters of soft, glowing glass down through the holes, creating a row of sagging glass bubbles hanging below the track. Next, a synchronized line of water-cooled blowheads drops down from above, matching the exact speed of the moving ribbon. Each blowhead shoots precise puffs of compressed air into the sagging glass blisters, expanding them downward. Above the lower track, hinged cast iron molds lined with wet carbon paste surge upward to clamp around the expanding glass bubbles. The molds spin at high speed around the glass as compressed air presses the soft bulb against the mold walls, polishing away every seam line until the glass shell is completely smooth. Mechanical speed replaced human breath with astonishing power. While a skilled human crew produced 300 bulbs during a full day of work, the Corning ribbon machine spat out 2,000 perfectly uniform light bulb envelopes every single minute. A single ribbon machine produced over 1 million light bulbs in 24 hours, instantly slashing the cost of an electric bulb from $1 down to pennies. Corning supplied 90% of all light bulb envelopes on Earth from a single factory floor, turning dark cities into bright glowing beacons. Cheap light bulbs were not Corning's only major breakthrough during this booming era. Around the same time, a Corning chemist named Jesse Littleton brought home a sawed-off battery jar made of an experimental heat-resistant glass called Non-X. His wife, Bessie Littleton, baked a sponge cake in the glass container, discovering that it baked faster, cooked more evenly, and washed clean easily. Corning refined the formula and launched Pyrex in 1915, conquering home kitchens and scientific laboratories across the globe. Conflict across the world pulled Corning's heavy iron foundries and specialized glass formulas to the front lines. During World War I, America found itself cut off from German optical glass, threatening the production of military submarine periscopes, artillery rangefinders, and aerial survey cameras. Corning engineers worked grueling night shifts in dust-filled batch rooms to create high-purity optical glass formulas that freed the nation from foreign dependence. By World War II, factories ran 24 hours a day to manufacture cathode ray tubes for radar screens, high-altitude aircraft nose cones, and heavy glass insulator bushings for military radios. Casting the largest glass telescope mirror in human history became Corning's ultimate test of engineering nerve in 1934. Astronomers commissioned Corning to cast a massive 200-inch telescope mirror disc, weighing 20 tons for the Hale telescope at Palomar Observatory. Casting 20 tons of boiling Pyrex glass into a single-ribbed disc had never been attempted by anyone on Earth. Corning constructed a giant specialized furnace, nicknamed the White Elephant, where workers poured ladles of boiling Pyrex at 2,800 degrees into a ceramic mold held down by heavy iron core anchors. Disaster struck during the first pour when extreme heat melted the heavy steel bolts holding the core molds down. Core blocks snapped loose and floated up to the surface of the white-hot glass-like corks in boiling water, ruining the 20-ton disc. Refusing to surrender to failure, Chief Physicist George Macaulay redesigned the entire mold anchor system, using internal water-cooled steel pipes to preserve structural strength under extreme heat. On the second pour attempt, the liquid glass filled the mold perfectly. Workers transferred the giant glass slab to a special annealing oven, where its temperature was lowered by a fraction of a degree each day for 10 full months to eliminate internal stress. That 20-ton slab of Pyrex outlived the war and remains fully operational at Palomar Observatory today. Water posed another deadly challenge in June of 1972, when Hurricane Agnes triggered catastrophic flooding along the Chemung River. Brown River water breached protective dikes, submerging Corning's primary factories under 5 feet of thick mud, silt, and river debris. Precision machinery rusted, electric motors shorted out, and decades of scientific archives were swept away. Wall Street financial analysts predicted the company would take years to rebuild its lost production capacity. Stripping down rusty iron machines with kerosene, local factory workers waded directly into 5 feet of muck. Machine operators hand-scraped precision lathe tracks, rewound water-damaged electric motors, and fired up giant glass furnaces in just a few weeks. They proved that upstate New York industrial grit could overcome any natural disaster. Copper telephone wires hit a physical wall by the late 1960s. Heavy copper cables beneath city streets were clogged with electrical signals, unable to carry the vast amounts of digital data needed by early computer networks. Electrical engineers knew that light waves could carry thousands of times more information than electricity through copper wire, but light needed a perfectly clear pathway. In 1966, researchers suggested using thin glass threads to guide light signals, but existing commercial glass absorbed so much light that 99% of the signal disappeared within just 60 feet. Glass researchers Robert Mora, Peter Schultz, and Donald Keck stepped up to solve this telecom bottleneck. They realized that traditional glassmaking methods, melting raw sand in clay crucibles, introduced tiny metallic impurities that absorbed light particles. To eliminate those light-blocking impurities, they abandoned traditional furnace melting entirely and pioneered a process called outside vapor deposition, or OVD. Burning liquid silicon tetrachloride and germanium tetrachloride inside a high-temperature gas torch allowed them to deposit ultra-pure glass soot particles onto a spinning ceramic rod. This process built up a pristine cylinder of glass soot. Heating the soot cylinder turned it into a clear rod of fused silica, which was then pulled through a vertical draw furnace into a flexible glass thread thinner than a single strand of human hair. Testing a new glass fiber sample on an August afternoon in 1970, experimental physicist Donald Keck focused a laser beam into one end of the thin fiber thread. He watched the light detector needle at the far tip. To his amazement, the needle barely moved, proving that light traveled through the glass with almost no signal loss. Keck checked his instruments, ran the test again, and verified a world-changing breakthrough. In his laboratory notebook, he scribbled a famous phrase, 17 dB/km. Eureka! Corning had invented the world's first low-loss optical fiber, solving the telecommunications bottleneck forever. Federal agents raided the Upstate New York plant in 1982 because foreign conglomerates realized Corning's optical fiber patents gave them a monopoly over global communications. Espionage rings tried to steal secret mechanical prints of Corning's vapor deposition burners, fiber draw towers, and tension controls. Corning prosecuted the theft in federal court, winning landmark patent judgments that protected American manufacturing dominance. The mystery of the FBI raid was solved. Those seized glass spools held the secret physical keys to the modern internet. Wild financial speculation nearly destroyed Corning 2 decades later. During the late 1990s dot-com boom, Wall Street became obsessed with optical fiber. Telecom companies laid millions of miles of glass cable under streets and ocean floors, pushing Corning's stock price to an all-time high of $113 per share. Corning responded by investing billions of dollars into new fiber draw towers, clean rooms, and optical component factories. Then, in 2001, the telecom bubble burst with crushing force. Tech companies went bankrupt overnight, leaving millions of miles of optical cable buried underground unused. Demand for fiber evaporated instantly, and Corning's stock plummeted by 99% down to a humiliating $1.45 per share. Wall Street restructuring firms and short-term financial analysts descended on upstate New York like vultures. They advised executive leadership to follow the standard corporate playbook: shut down historic foundries, fire research scientists, sell off precision machine shops, liquidate intellectual property, and turn Corning into a low-cost importer of cheap plastic parts. Private equity raiders argued that hands-on glass research was an obsolete money pit in an era of digital asset management. Executives at Corning made a courageous decision that defied corporate greed. Having survived the Great Depression, 2 world wars, and the devastating flood of 1972, leadership refused to dismantle their physical engineering heritage. They cut overhead expenses aggressively, but protected their core team of material scientists, master glassmakers, and precision maintenance crews. They kept their glass furnaces idling and maintained their high-precision draw towers. Phone maker Steve Jobs called Corning in 2006 while preparing to launch the original iPhone. Jobs realized that plastic smartphone screens scratched too easily under daily use, and he needed an ultra-thin, highly durable, scratch-resistant glass cover. Corning scientists searched their archives, pulled out an abandoned 1960s chemical strengthening formula called Chemung, and retrofitted factory lines in just 6 months to mass-produce Gorilla Glass. That refusal to surrender to Wall Street speculation created a billion-dollar market that now protects mobile screens across the globe. Financial bubbles inevitably burst, corporate raiders fade away, and paper stocks rise and fall in digital ledgers. Yet heavy iron, materials science, and fundamental physics refuse to yield to short-term quarterly earnings reports. The legendary Corning ribbon machines ran continuously for over 70 years without stopping. Born in the Roaring '20s, they spat out billions of lightbulb shells with cast-iron reliability before being retired to museums. Today, ultra-pure fused silica fibers drawn in those upstate New York towers lie silently on cold ocean floors, carrying more than 99% of all global internet traffic at the speed of light. Every email, video stream, and online search relies on a microscopic glass thread forged in a quiet river valley by craftsmen who mastered heat, pressure, and material purity. The iron outlives the empire. Looking for more forgotten industrial sagas and heavy engineering history? Click the video on your screen right now to discover how massive steam machinery forged the greatest canal system in human history. Don't forget to like, subscribe, and drop a comment below to support Rivet and Rebar.